Today, we will go into a bit of detail on two of the most popular thermodynamic systems, refrigerators and heat pumps, and also see how these relate to the second law of thermodynamics. We saw in the last video that hot objects cool down, and essentially by nature, objects attempt to equilibrate to the same temperature. So then, how do refrigerators work? This requires an input of energy. The most common type of refrigerator is a cyclic device using the vapor compression cycle. This involves four main components. Work is put into a compressor, which both heats and compresses the working fluid. Energy is then rejected to a hot reservoir, usually the surrounding air, hot being a relative term. This cools the working fluid usually into a liquid without changing the pressure. The fluid then moves through an expansion valve, usually a capillary tube, which both cools and expands the fluid to a lower pressure. Energy is then added from a cold reservoir in the evaporator, which takes the fluid back into the vapor state, but more importantly, removes energy from the refrigerated space. The fluid then enters the compressor and the cycle continues. As a real-life example, the fridge in your kitchen uses the freezer compartment as the evaporator, and the coils behind the fridge serve as a condenser. Because of the somewhat strange effect of this cycle cooling part of the surroundings, the standard measure of efficiency doesn't entirely make sense. Instead, we use something called the coefficient of performance. What we are trying to achieve is cooling of the refrigerated space. This is done by adding work to the condenser. So the coefficient of performance is given by COP equals QL divided by W net in. We use a subscript R on COP to specify that this is for a refrigeration process, and W net in is equal to QH minus QL due to the first law for cyclic processes. Also, this ratio can actually be greater than 1. This is the big difference between COP and efficiency. A very similar device to a refrigerator is a heat pump. These also transfer heat from a low temperature reservoir to a hot one, but they serve the opposite purpose. Here we are trying to heat up the hot space associated with the hot temperature reservoir. In this case, energy is taken in by the low temperature reservoir as well as work into a compressor. So this is essentially exactly the same situation as we just saw for the refrigerator. The only difference is in what we are trying to accomplish. Rather than cooling down a cold area, we are heating up a hot space. Therefore, the only difference is in the coefficient of performance. Just like efficiency, it is a measure of what we are trying to accomplish compared to what is put in. So instead of the cold heat transfer for a fridge, for a heat pump, we are looking at the heat transfer into the hot space. So here, the COP is equal to QH over W net in, or QH over QH minus QL. And again here, we have a subscript H on COP to distinguish it from the previous one for the refrigerators, the only difference being the numerator, QH instead of QL. The two are related though, through the fact that the net work in is equal to QH minus QL due to the cyclic nature of the process and the first law of thermodynamics. So it turns out that COPH is equal to COPR plus 1. Looking at this, it can actually be seen that COPH must always be greater than 1. You also sometimes see the performance of air conditioners given in terms of an energy efficiency ratio. This is simply a constant value of 3.412 times the coefficient of performance, COPR, air conditioners being essentially refrigeration units. So far, the only version of the second law of thermodynamics we have seen essentially stated that we need more than one reservoir. A second version of the second law of thermodynamics is called the Clausius statement. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature body to a high temperature body. This basically implies that heat only naturally moves from hot to cold objects, which we kind of already knew, but is now stated in the form of a law of thermodynamics. It also implies that if we want energy to flow from cold to hot, it is possible, but we need some sort of energy input. This form of the second law is actually equivalent to the one we saw in the previous video. and so both are called the second law of thermodynamics. You have probably heard of perpetual motion machines. This is any device that either keeps moving or moves faster without any net energy input. Unfortunately, these either violate the first or second law of thermodynamics, or sometimes even both. Creating energy is impossible by the first law. These are perpetual motion machines of the first kind and are ones that speed up. Any device that violates the second law is called a perpetual motion machine of the second kind. These are devices that remain moving at the same speed without any energy input. The most common forms of these exchange heat only with one reservoir, violating the second law in the form seen in the last video. This brings us to reversible and irreversible processes. I have used the example of a warm cup of tea cooling down a few times. This is an example of an irreversible process. It is irreversible because the tea will not spontaneously heat up in a colder room. Any process that is irreversible has no effect on the surroundings. Both the system and the surroundings need to be unaffected for this process to be reversible. The only way this is possible is if the net heat and the net work for the process are both zero. This is for the entire cycle, or the combined forward and reverse processes. Any situation where this is not the case will by definition be irreversible. It is possible to return any system to its original state. It is whether or not heat or work need to be added which determines whether this is reversible or irreversible. Unfortunately, in real life, there is no such thing as a reversible process. There is always some sort of inherent inefficiency or energy-sucking process occurring. However, some processes are pretty close and can be approximated as reversible. Reversible processes must contain no inefficiencies and therefore can represent an ideal scenario to which all other processes can be compared. As such, reversible processes will always either deliver the most work or consume the least amount of energy. There are a lot of causes of irreversibilities in real life, things like friction, mixing, heat transfer, and many, many more. So to have a truly reversible process, we need all of these things to be absent, which does not happen too often. The main problem is that many of the processes lead to the conversion of useful energy to heat. Any form of heat causes a temperature difference, which leads to heating or cooling, which we already know is an irreversible process. So one condition for an approximation to an irreversible process is to have a negligible temperature difference. Now, just to be super confusing, there are differences in entire cycles being irreversible and individual processes being irreversible. This leads to the distinction between internally reversible, externally reversible, and totally reversible processes. Internally reversible processes essentially are just looking at what is happening inside the system. In other words, having no irreversibilities inside the system. Externally reversible processes look at what is happening to the surroundings, no irreversibilities outside the system, while totally reversible processes are a combination of the two. This is also just called reversible. So if something is called reversible, it is referring to both the system and the surroundings. Well, we've now reached the end of today's video. So here is the pre-lecture example for you to try out, as well as the answer. I will hopefully see you all in class later and answer any questions you may have.